So this is on already.
It's on already. All right, folks, we need to get started. So I see people coming into the room. We'll pause for a few seconds, but only a few seconds. Your speaker? Who's that? Where's our, your speaker? Okay, come on up. All right, we are going to begin this second session of the morning here on Saturday on wastewater treatment and other bioremediation applications. I'm Bruce Rittman. I'm the director of the Swedish Center for Environmental Biotechnology here at ASU, your host. And I'm joined in the room by a number of other center people who are going to be helping us. We have Michelle and Deanna and Joe and I think Mohammed and Sean. We got all kinds of people here helping, and I want to recognize them. Okay, I think we need to get going here so we can keep close to the schedule. Our first speaker, standing to my right, is Boris Tartakovsky from the National Research Council of Canada, and he's going to talk to us about COD and nitrogen removal, and you're on.
Thank you for pronouncing my family name so well. These are our most recent results on combined COD and nitrogen removal. Here, just to mention, we are this project was actually initiated as a part of the Arctic program at the National Research Council of Canada. It's a big program targeting different areas of engineering, different engineering solutions in things like environmental remediation, resource exploration, but also infrastructure. And of course, wastewater treatment is a part of community infrastructure. That's how the project came to life. First of all, we're talking about remote communities, wastewater treatment needs for remote communities, also in the Arctic. So the requirements are somewhat different, and I wanted to mention those. For one thing, many communities are on water delivery, which means that there is a truck going around every day or two delivering water. And then sewage is also collected by a truck, hopefully by another one, and that results in a very low water consumption, about 3 times less than under normal circumstances. So about 100 liters per person per day, and that means that sewage is quite more concentrated, maybe around 1 gram per liter. COD concentration. Then electricity is very expensive, up to $1.50 per kilowatt hour. It's hard to service complex systems and hard to maintain them. Communities are very remote, and also temperatures, of course it's Arctic, temperatures are low. So that means that an ideal system for wastewater treatment in this situation should consume as little energy as possible, and energy production is very interesting. Should be very simple to operate and to maintain, and also should work in a broad range of temperatures, including low temperatures. So we thought that bioelectrochemical systems could work in this situation, and that's how we started. We decided to compare microbial fuel cells and microbial electrolyzer cells, keeping in mind that the objective is not electricity production or hydrogen production, but simply wastewater treatment, and preferably combined carbon-nitrogen removal. So we used our more or less standard system that we have developed over time. In MFCs, it means carbon felt cathode, no membrane, 50 milliliter cathode anode compartment, continuous flow at about retention time of 8 hours, so 2 pumps feeding nutrients, carbon source and dilution water and continuous effluent. For MEC, it meant the same carbon felt anode, but also because we were not interested in hydrogen production, it's again single compartment system with biocathode, again carbon felt. No membrane, again, just non-conductive separator, synthetic cloth, essentially. So we used acetate or wastewater as a feed, and of course, in Montreal and in April, it happened to be really diluted, less than 200 milligram per liter CODs. We had no choice. Some results here. I forgot to mention that we had to compare under optimal conditions for both systems. And so for MFC, it meant that external resistor had to be in real time adjusted to match internal resistance. We used the perturbation observation algorithm. For MEC, it meant a real-time adjustment of applied voltage. So we basically maximized the current within the given range of voltages, of course, to avoid water electrolysis. So these are our results. You can see that we started with this is COD removal, starting from acetate. So we operated two systems in parallel in several phases. They are more or less identical. And you can see that at the beginning, at about 1 gram per liter acetate influent, the removal was complete in MEC, in MFC. We doubled the organic load, and in that case, we did observe effluent acetate different from non-detectable level. That would be used to calculate maximal removal rate. Then we had two phases, 3 and 6, where we would only feed ammonium. Then we also had phases of OCP operation for MFC. It's between 5, 6, and 7 to compare, and you can see that COD removal really decreased in that case. Interestingly, even in this phase of CP operation, we didn't observe any methane production, and in other phases as well, which means basically that the conditions were optimal when the electrical circuit was closed, so we would expect high Coulombic efficiency. But also that means, since we don't have membrane, that during the open circuit operation here, most of removal was aerobic, simply because of oxygen diffusion through the gas cathode. So also the same was done for the MEC, so you see that removal was very similar. Startup was a bit faster as well. We also, when we increased in the organic load, we observed acetate in the effluent. Again, ammonium phase, 0 voltage phase to compare, and here, throughout the operation, we didn't measure methane, we didn't measure hydrogen production. Instead, we observed methane because there was no separation between the two compartments. So everything goes into methane through hydrogenotrophic methanogenesis. One interesting, actually two interesting phases, 5 and 6, were phases where we created microaerobic conditions in this system by simply adding a little bit of hydrogen peroxide to the influent. Hydrogen peroxide quickly decomposes into oxygen, and so we don't measure dissolved oxygen. It was undetectable, but we knew that microaerobic conditions were present. And once we doubled in phase 6 the amount of hydrogen peroxide, we've seen a clear decline in the MEC performance. So these are maximal removal rates for the two systems. Ammonium removal, this is kind of more interesting. In MFC, we had about 55% COD removal, ammonium removal, no nitrate or nitrite. Now, when only ammonium was fed to the system, the removal really, it's phase 3 removal really was observable, but very low. And in the open circuit mode, here, phase 5, there was no removal, as well as no removal with or without carbon source. So MEC was operated in a similar way. However, there was no removal, or very small amount of ammonium was removed during operation on acetate and ammonium. Of course, no removal when only ammonium was fed, and no removal when voltage was 0. However, during the microaerobic phase, which is phase 5 here, we observed up to 33% removal. So it kind of matches conditions in the microbial fuel cell. Again, once we oversupplied oxygen, even oxygen was not really detected in the MEC itself, the removal decreased to near 0. So these are, so that's the dissolved oxygen effect. And ammonium removal rates were somewhat better in MFC as compared to MEC. Another interesting observation for the microbial fuel cell was that during this open circuit operation, we observed nitrite and nitrate in the effluent, but not during other phases. And the last phase was on real wastewater. So it was kind of reasonable, but not better, of course, than in the period of acetate operation. Electrochemical performance, in terms of current densities and Coulombic efficiencies, the results were in agreement to material balances. Don't forget that these are per liter of reactor volume, and MEC was 2 times bigger. So if you see current densities, actually they're different here, but per anode volume, they would be very much comparable. Coulombic efficiencies were also comparable, and pretty much between 60–80%, which is apparently due to optimal operating mode. Interestingly, in the microbial fuel cell during ammonium-only test, we observed non-zero current and calculated Coulombic efficiency at around 27%. So it's measurable. There was no, so these are OCP tests. So there is no removal in MEC in the absence of oxygen, but when microaerobic conditions were created in phase 5, you can see performance, electrochemical performance was not very different, for instance, from phase 4. Somewhat decreased the Coulombic efficiency, but that to be expected. Phase 6, when we over-aerated, it really shows that there was too much oxygen. Overall, we can say that it appears ammonium removal is really controlled by oxygen, and there's a very narrow band of acceptable operating conditions. If you have too little, it doesn't work. If you have too much, you inhibit anaerobic microorganisms. Here are, okay. So the next part is analysis of energy production or consumption for the MEC. So you can see that energy production in the microbial fuel cell was reasonable at around 60 watt per cubic meter, but overall it's quite low. So it doesn't seem to be justifying the complexity of microbial fuel cell with the gas diffusion cathode and so on. And MEC, it was a little bit better, but in terms of energy consumption, 2 to 4 watt-hour per gram COD, but still quite high. And we attribute this to actually inefficient design. We used biocathode, and it was kind of a little bit to the side of the flow. So we believe that could be improved. Of course, if you consider methane production, that offsets somewhat energy consumption. So instead of, say, 2.4, you get 1.7, but it's still high. pathways. We didn't do any biomolecular work, so we just can hypothesize, but the idea is, of course, we had anadophilic bacteria to remove acetate. We had conventional nitrification and denitrification. We probably had, at least we can hypothesize, heterotrophic nitrification and anamox. But most interestingly, it's these two reactions, because we didn't observe ammonia, we didn't observe nitrate-nitrite for most of the experiments, and we also didn't see much, volatilization could be considered, but was unlikely. So we hypothesized that we did have direct ammonium oxidation coupled to nitrite reduction at the cathode, something that should be studied more. To conclude, we had reasonable COD removal rates in both systems, but ammonium was much less reliable, 50% at best, and required microaerobic conditions. So also we think that flow-through electrodes might decrease energy consumption and MECs, so the net could be at the end could be positive if methane is considered. And then we continued those tests with MFC-based reactors, MEC, microbial electrolysis cell-based reactors. That's just to give you a taste of what currently is going on. The reactor is covered not really to hide the inside structure, but because we needed to insulate it. Some of the tests, like currently it runs at 5 Celsius, and so we needed good thermal insulation. It seems with this, it's about 20-liter reactor with this design. It seems that we are able to achieve a reasonable performance, and so we're planning to scale this approach, flow-through electrodes, microbial electrolysis cell, to first around 100 liters, and then a couple of cubic meters in the next year or two. That's all.
Okay, thank you, Boris. So I think we have time for one question. If you have a question, identify yourself. While the question, there's Hyung-Soo Lee has a question. Okay, and while this is going on, Deanna, are you taking care of this? Okay.
Thanks, Boris. One quick question about ammonium nitrogen removal mechanism for MEC. What would be mechanism for ammonium nitrogen removal in MEC, not MFC?
Both
Come
systems.
Boris,
Yeah.
come here around here.
We think that there were parallel reactions happening, I won't exclude something related to denitrification based on methane consumption, for instance. But it appears that if a small amount of oxygen is present, one of possible mechanisms is direct ammonium oxidation at the anode, which requires a little bit of nitrite, and that's where oxygen plays its role. You need coexistence of conventional nitrification to produce a little bit of nitrite by nitrous ammonium, and maybe direct oxidation. So, because without nitrite, it just cannot start. So that's, let's say, mechanisms of interest, although everything else cannot be excluded at this point because we didn't do any biomol work. It was kind of practically oriented project to see what is our material balance.
Okay, all right, let's thank Boris again. Jason?